lateral force act, this column tends to deflect like this. This deformed shape we will discuss later. This is the amount of delta that is displaced. Now, if we see the movement here, the movement will be F into L. The effect of this deformation is not counted here. This is first order analysis. Whatever we study in bachelor's or in course till now, that bending moment, axial force, shear force diagram, these are the result of first order analysis only. But when this member is deflected and the gravity force also, point of application also shift towards here. Now, if this point is deflected from this member is getting force from this point, now additional moment will be created here. If you see this at this point, now F into L plus P into delta. If this delta is the amount of deflection, this is first order analysis and this is second order analysis. So if you see this P delta is the extra moment we get after, due to the result of this deformed shape. Without deformation, we will not get this effect. After this column deflects and it deforms, the point of load of action also shifts, and this amount of the displacement is occurred, and then extra moment we get. This is P delta here. This is known as second order analysis, and this for the result when we get without deformation of structure, this is first order analysis. If we go through the definition, this is the default behavior that we get if we don't consider geometric nonlinearity. This is known as linear analysis or elastic first order analysis. But the second order analysis is the result of deformed structure. This is also called second order analysis. We call this second order analysis because we are considering deformed shape while writing the equilibrium equation. So we are actually considering this as a geometric nonlinearity. Now, main point here is, do we get always higher moment if P delta, if you are considering P delta analysis? This might be a question, but sometimes what happens is, when here in this figure, if let's see in this figure, let's first I like to clean up this. If we are designing a column with tensile load and lateral load. Now, if you see here, what will happen is, this is deformed is like this. Point of application is here. L is this. P is this. Let's give same notation. Deformation is also delta. Now, what happened here is, for the force that is not compressive, for tensile force, the moment will be here F into L minus P is acting in anti-clock direction, so it will be minus P into delta. So the P delta always won't give us higher moment or higher forces. It may reduce also sometimes. So we need to understand that part also while designing. Sometimes what happens is, while we are designing some member, rather when we consider P delta analysis, rather of coming more force, sometimes it may reduce. This is due to this effect. So if we see here in definition, it is important to understand that in our example above, the axial load was compressive. Here P was the compressive force. So it has increasing effect on the response, like bending moment and displacement. This is also known as softening effect. When the compressive force is acting, the P delta effect creates softening effect. However, if the load is tensile, it would actually decrease the bending moment and displacement, which is also known as stiffening effect. We need to understand this part. Sometimes, while interpreting the results, it may get we may get confused. We are considering extra moment, but we are getting lesser rebar or lesser force. So we need to understand this also. There are two type of P delta analysis. If we see, uh, there is a P small delta and P big delta. P, so far we have discussed now till now is P is big delta effect. This represent the lateral deformation at the top relative to its base. This phenomena is also referred to the global or large delta. This P big delta is the global effect. Now, in addition to big delta, there is also a small delta, which is the deflection of column locally. It is local effect. Now, here, if you see, the deflection should be in straight manner, right? Straight line. But the deformation is like some curve due to its stiffness, like you can say some buckling also. This bending creates this curve pattern. This gives additional moment here. This is our first order moment. Here, horizontal force is denoted as H, and height is denoted as small s. This is first order moment. This is P delta, which is second order moment, and additional delta while designing column. We get P small delta due to its further deformation. This is known as P small delta. Now, while designing in analysis model for P big delta, we define some parameter and then extra work we have to do in model. But this P small delta is considered by default from in software. If you see IS 456 clause number 39.7, here it is written that, but to capture P small delta, the effect during actual column design amplification factor is used as given in code. It is written. This is considered by software itself. This is the amplification factor that this is the formula that software use to consider additional moment due to P small delta. So this is an iterative process also. We need to understand that when P delta occurs, this is the deflection due to horizontal force H. Now, when this point at this point, when the column is resisting in vertical manner without deforming, it will only give compression force. It will not laterally deflect. But when the force is acting at inclined member, it will further tend to deflect more. So this P delta is an iterative process. We do this. The software does this part is until it converges the difference between both results. First, H delta H into L plus P into delta. Now, after acting this P delta, this member again will further deflect by small pattern. Again, it will P delta dash till the difference between this point are within our convergence limit. This process is iterative. It will continue. We need to give that convergence factor in ETABS also. Until that it converges. So we need to understand that P delta is a iterative process also. Now that was the theory part. Now we will understand that how it is done in software, then how software treats its and also what are the process of doing this P delta analysis, what are the method, how many types it gives, how many approaches we have to do in P delta in ETABS. There are two methods in ETABS to perform P delta analysis. One is non-iterative based on mass, in which load is automatically computed from the mass at each level. Generally, when we design a building, even though we model it as a 3D model like this, it converts the building into lump mass method. It will be act as a single column. The lump mass will be acting at the center of mass. These will be from this pattern. ETABS takes the building while analyzing. Now, when it deflects, it consider this mass as a this mass is computed while doing P delta analysis in this first method, which is non-iterative based on mass. This is not a iterative solution. It does just take one step solution. Just we did P into delta only. The effect of this load again is not considered in this method. It is most effective when with a single rigid diaphragm at each level. The building is pretty simple, and we can apply a rigid diaphragm. In this type of building, this P delta analysis, this non-iterative based on mass method is suitable. In this analysis, the local buckling is not captured as effectively. That P small delta effect is not captured effectively in this type of this method. But what happens here is the benefit of this non-iterative method of P delta is it doesn't consider gravity load cases, so it takes lesser computation time. It is not iterative, but when gravity load is specified, the iterative based on load cases method is generally recommended. Main point here is what is every code, every seismic code gives some factor to consider the gravity load to be considered while doing P delta analysis. So while doing real project, we do not follow this project, this approach. We follow this approach. In this method, it is iterative based on load cases. In this method, load is computed from a specified combination. You need to understand this combination first. We'll see that combination in next slide of static load cases. Then known as P delta load combination. That combination is known as P delta combination, and this is an iterative method which considered P delta on an element by element basis. Local buckling is captured more effectively. An example application may be when load include dead load case and fraction of live load case. Now let's see. We have Indian code, new Indian code. I think it was introduced in 2017 or like this. Before that, this code was not released. This code is for high-rise or tall buildings. So this tall building gives in 7.2 clause number 7.2. The load combination for initial analysis considering P delta effect shall be taken as 1.2 dead load plus 0.5 live load, and this part is 1.5 earthquake load or wind load. The load factor, that load set of load cases while defining P delta is used this, and while whole designing load combination we have to define this load combination also. Right now, how it is done in ETABS? Let's see. All other steps while we design in static analysis and designing part are the same. I have just demonstrated here what additional tasks to be done during doing P delta analysis. For this, we have to go to define in ETABS. Let's go in ETABS itself. Just a minute. This is a reference model I have created to this class. We need to go to define here, and here is P delta option. For this, let me unlock this model first. We go to define P delta option. Here is one is none. If we click none, then it will not consider P delta effect in this building. Another is non-iterative based on mass. This is not recommended while designing real structures, and iterative based on load. Here we define this from this drop down. We need to select those load cases. This dead, live, this wall, floor finish also come under dead load. So I have given the factor dead 1.2, wall 1.2, floor finish 1.2, and live load is 0.5. Before I have talked about this convergence tolerance. Yes, this is iterative. Until the result from two consecutive results, the difference of two consecutive results are lesser than this value, with the software iterate, analyze again and again. But sometimes if the building is too much complicated and too much huge, this higher convergence, if we provide this higher convergence tolerance, the model ETABS cannot converge it. So sometimes we have to reduce this convergence tolerance also. We need to understand that sometimes we need to do that trick also. Then after defining this, now load case, if we check load case, in each and every load case, there will be P delta option here. P delta or nonlinear stiffness. Use P delta preset, P delta setting. It is coming here, iterative based on load. If we keep this none, it will come none. So if we have defined this P delta iterative based on load, it will consider by itself. Only this additional work we have to do during P delta option, the P delta analysis. And one last thing is to be done in ETABS is we need to go to the if we are designing steel frame building, we need to go to steel frame design. If we are designing concrete frame design, we need to go to concrete frame design and view revised preferences. We need to check this, consider P delta done, and is to be yes here, and consider additional moment, that additional P small delta, we need to keep both yes. Then the software will itself do this P delta analysis. Now let's go back to our slide. These are the process I already demonstrated in ETABS. This one. Now let's compare the result. I have already run that model and check what is the difference. If we see the deflection, what is the total deflection of the building due to lateral load before P delta and after P delta analysis is activated. Before P delta, when we check the top displacement at this point, we are getting 54.6 mm. After P delta, we are getting that deflection is 57.667. This is due to the additional force, and that P is acting when just a minute. At this point, while designing building, it doesn't do same as like column. there somewhere in between center of mass, the this all mass is lumped. At that point, the point is acting like this, and this force also further deflect this building. And another consideration is already big delta we are considering. Now if we see the forces here, before P delta we are getting in this, these are the same building, we are getting 139 kilonewton meter movement here, but after P delta the force is increased to 147. So there is a significant difference, even though it is a symmetric building and not too much high rise. We are getting some more movement, but for high rise and tall building, it will give a significant difference. So we have to always consider P delta analysis during design. Now there will be one question: up to which building we need not to consider P delta analysis, and after which we need to consider P delta analysis. Generally, the Indian code does not speak about this parameter, but when we go to Euro or AISC code, they give a stability index. We need to calculate that stability index. When there is a certain factor, when that is when that factor exceeds to the limit, then that we need to consider P delta. Otherwise, we don't need to consider P delta. But in general practice in professional field is up to 10-story building, the P delta effect is not much that significant that will change the design and result. But when it crosses 10-story and above, 10 to 20-story, there is significant effect, and before after 20-story there is a crucial important, we should not miss this P delta analysis after than that. So in summary we can say that after 10-story we need, if we consider P delta analysis, we will be in safer side. So we can conclude this P delta analysis at this slide. We will do Q&A session after this whole session. So I would like to continue for diaphragm first. Now let's discuss about diaphragm. Diaphragm, what is diaphragm? Diaphragm is generally we can say slab as a diaphragm. To visualize in a layman's language, we can say diaphragm, the slab act as a diaphragm. So let's go through the definition first. Diaphragm is a structural element that transmit lateral load to vertical load resisting element of a structure, such as shear wall, column, and braces. These diaphragms are roof, floor, or other member or bracing system, horizontal bracing system. I mean to say this horizontal bracing system. If you see in PEV structure, truss type of structure, this horizontal bracing system acts as diaphragm. They help to transmit horizontal that horizontal load, lateral load to vertical resisting element system. Diaphragm are typically horizontal but can be sloped in a gable roof or wood structure or concrete ramp in parking garages. Diaphragm play an important role in distribution of seismic and wind force towards the force across the structure, ensuring that the loads are transferring efficiently to the building's lateral force resisting system. If we see a building here, lateral force from some formulas, if I start to talk about those formula, it will take more time. We will not be able to conclude this session. So just I jump towards the result. Base shear is acting at this point. This base shear is distributed with some pattern of formula Q1, Q2 is a story shear, Q3. This force is acting at center of mass. And this center of mass, if we see in plan, Here is column, here is column, here is column, here is column, here are columns, 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 columns. This point is this load is acting at this point, let's say. Now this load is to be distributed in this vertical load resisting system. This work is of diaphragm. Diaphragm transmit or distribute the load in a specified manner. What is that specified manner? The type of diaphragm defines that specified manner. One is rigid diaphragm, another is flexible diaphragm. To understand diaphragm, we need to know about a joint first. There is a restraint joint, another is constraint joint. Restraint joint are like support system. I'll go in just brief about them. These are support system. This might be fixed, hinge, or roller that are related to only one joint. If you see a building, the last point is joint with foundation with single element. But when the building, if we see the building plan, this column, this column, this column, this column are interconnected by different joint here. These are constraints. The constraints are also of different type, but this constraint we use in building is diaphragm constraint. So in summary, what we can say is restraint joint are like applying a boundary condition in a single point. This is directly related to soil, or like it is support condition. Constraint joint are like applying a boundary condition between group of joint. Let's understand this part. If we understand these two paragraphs, it will be more clear about diaphragm. In general, a node has 6 degrees of freedom. We know that 3 are translation x, y, z, and 3 are rotational in x, y, z direction. Translation and rotational. Before applying any constraint, so if a structure, let's say slab, has 10 nodes, let's say we have meshed this building as a this slab as a 10 to create like a 10 nodes. This means the total degree of freedom in this structure is 60. But when the constant is assigned, the degree of freedom is reduced. Now, when we assign some parameter like that, every point in this slab in x direction deflect with same value, then this 10 degree, the total 60 degree of freedom we have initially. Now what happens is only 1 degree of freedom in x direction, translation x direction is happening here. Then we can say that 60 minus 10 plus 1, this 1 x direction is available. It is coming to now 51 degree of freedom. Now again, if we restrict or assign such that like every point in y direction are also moving in same point, same value, then again 51 minus 10 plus 1, 42 degree of freedom are happening there. So this constraint and diaphragm works like this manner. So here no constant has been applied in z direction. We need to know that z direction we do not apply constant because deflection pattern might be like this. So the slab or diaphragm is not such more effective that it acts as rigid and it does not deflect in its outer plane action, but in plane action it is too much rigid so that we can consider it is rigid and it deform in same value as a whole, because it depth we know stiffness that b d cube by 12, this depth is too much higher, so it acts as a rigid. So slab can still have 10 different value displacement in z direction, where in this definition we have achieved rigid diaphragm. Now let's go through the type of diaphragm here. There are two type of diaphragms basically. One rigid diaphragm, one these two comes under flexible diaphragm. But when we see the research paper or something like all, there are only two definitions. One rigid diaphragm, another is flexible diaphragm. Rigid diaphragm assume that diaphragm is rigid compared to the vertical element, and lateral force are distributed to this element proportional to this their stiffness. What happens here is Now let's make this here. Here is a huge shear wall. Here is a huge column. Here is a small column. Lateral load is acting at some point. Now stronger element will take higher force and smaller element will take weaker element will take weaker in means of stiffness will take lesser force. This action is given by rigid diaphragm. But in flexible diaphragm, what happens here is it gives the horizontal force, seismic force is not acting as a single point or center of mass. It is acting wherever there are nodes. Either we have mesh slab, internal mesh, or external, we have divided it. It is acting in every point we have divided the slab. So this will create that the vertical element, that lateral load resisting element, will take force according to their tributary area only. Now, what is semi-rigid diaphragm? We discussed about rigid and flexible diaphragm, but what is semi-rigid diaphragm? The semi-rigid diaphragm is the something new that CSI ETABS has introduced. This in ETABS, what we can do is we can apply rigid diaphragm, we can apply semi-rigid diaphragm, or do not apply anything. In ETABS, only these two are defined. We cannot, we can omit applying this diaphragm. In this, when we apply semi-rigid diaphragm, generally, if you have gone through the course, we consider EX plus 0.05 accidental eccentricity. We consider there is a provision in code that while designing any building, even though there is no eccentricity, we have to design the building with 10%, 5% accidental eccentricity. In Nepalese code, it is 10%, so I missed that term. So in Indian code, it is 5%. Additional 5% eccentricity we have to design. So if we apply semi-rigid diaphragm in ETABS, this accidental this 5% eccentric force will be distributed towards all those points. But if we do not apply any eccentricity in any diaphragm there, this eccentricity will be omitted. So it is recommended that always apply semi-rigid diaphragm rather than not applying anything. We can do, if we apply rigid diaphragm, there will be acting as a rigid diaphragm. If we not applying diaphragm, it will act as a flexible diaphragm. But if we apply semi-rigid diaphragm, this accidental eccentricity will be captured in the analysis. So we analyze this part. We apply semi-rigid part. Now there is a question when to apply rigid diaphragm and when to apply semi-rigid diaphragm. We can apply semi-rigid diaphragm always, but semi-rigid diaphragm cannot be applied always. We have to see some codal parameter here. The code specified here is in a building whose floor diaphragm is IIT 93/2016. In a building whose floor diaphragm cannot provide a rigid horizontal diaphragm action in their own plane, the design story shear will be distributed to various vertical element lateral force resisting system considering the in-plane flexibility of the diaphragm. This means it will go to each and every mesh point and distributed to vertical lateral load resisting system is for their tributary area. The floor diaphragm shall be considered to be flexible if it deforms such that the maximum lateral displacement measured from the chord of deformed shape at any point of the diaphragm is more than 1.2 times the average displacement of the entire diaphragm. Here you can see this is 1 point, this is 2 points. The building, when we apply lateral force, the building deflects in such manner. Sometimes it may be, this point may be straight, but due to some eccentricity, this point and this point are different. So the average of these 2 points should be greater than average of this, 1.2 times average of this. Then we can apply semi-rigid diaphragm. Otherwise, rigid diaphragm can be done. The benefit of rigid diaphragm is this computation time of software. It is decreasing degree of freedom, right? We already so that computation time will be lesser. Usually, here in code itself, it is written that usually reinforced concrete monolithic slab beam floor or consisting of prefabricated or precast element with reasonable reinforced discrete concrete, at least minimum of 50 mm on floor or 75 mm on roof, with at least minimum of reinforcement of 6 mm bar, space 150 mm center as topping of a plant aspect ratio less than 3. So can be considered to be providing as a rigid diaphragm. What it is saying is the monolithic cast, generally for residential concrete building we do monolithic cast, beam and slab are casted monolithically. We can consider here as a rigid diaphragm. For another precast, we give here nib or something like that structure. We apply here precast slab, and we have to do topping here for finishing. This topping should be at least 50 mm and 75 mm for roof, and the mesh should be 6 mm rebar should be placed in 150 mm center to center. In that case, we have to we can do rigid diaphragm. Otherwise, we need to apply semi-rigid diaphragm. Just now, how it is applicable in ETABS. For seismic load, for rigid diaphragm, the accidental eccentricity is associated with autoseismic loading is concentrated and applied to the center of mass. And for semi-rigid diaphragm, accidental eccentricity is applied to every node. In node diaphragm, accidental eccentricity will not be applied to any node. Now, for wind load, for rigid diaphragm, loading is applied to the geometric center of mass. For semi-rigid diaphragm, for wind load, it is little bit different. It is distributed in 10 nodes. The ETABS itself find that 10 node, appropriate 10 nodes, and so that the summation of this force with respect to centroid will be equivalent to the lateral and torsional wind case. So, in rigid and semi-rigid, ETABS do such thing in seismic and wind load. During designing in ETABS, what we do is go to define diaphragm and add new diaphragm. There are two options, rigid and semi-rigid. Whether we check in that diaphragm which is desirable to us, seeing the building geometry and construction material or technique, we define and then select whole plan and then go to assign, cell and diaphragm, and we apply the diaphragm as D1, D2. We apply, then it is binded like this. Now in ETABS there are two options. One is joint diaphragm and another is cell diaphragm. Generally cell diaphragm is recommended because when we go to this figure, let's go to this figure. When we apply cell diaphragm, the slab is internally meshed, not divided. The whole this forces. Let's first go to the rigid diaphragm. In rigid diaphragm, as I earlier said, the whole lateral force is acting on a point. As this is symmetric, so it is acting on the center, and these are the resultant force that this element are getting. So this force is acting on a single point, and as per their relative stiffness, the force are distributed to all these elements. When we sum up this reaction, it will come to 60.16. But in semi-rigid diaphragm, the force is acting at each and every internally meshed or externally meshed structure. Where there are joint, internal or external, the force is acting there, and this resultant is shown in green and yellow color. This is acting as like this. When we apply cell diaphragm, the point load is acting in a such manner. This internal mesh also works. But when we apply in joint diaphragm, wherever there are joint, only their force will be acting. So it is recommended to apply semi-rigid, this cell diaphragm in ETABS. Now main point to remember here is the base shear and estuary shear due to earthquake load remain same across the cases, whether it is rigid, semi-rigid or no diaphragm. The acting force will not and resisting force will not differ, but the distribution will differ. When earthquake load is applied on based on diaphragm, rigid diaphragm, it is taking at the center of mass. No diaphragm semi-rigid, it will take earthquake force are applied at each internally and externally mesh joint, and semi-rigid and no diaphragm is allows the application of eccentricity which generate moment at each joint. In if we don't apply diaphragm, then eccentricity cannot be applied. So moment are generated at no moment are generated at this joint. So it is recommended to recommend assigning a semi-rigid diaphragm unless you are certain that the floor processes very high in plane stiffness, in which if there is a very high stiffness, we can apply rigid diaphragm there. Now, semi-rigid diaphragm can, while in practical problem, sometimes what happens is if there is a lot of opening in the building, in the floor, and like I'll just try to demonstrate another part. I'll show you ETABS here. Thus, like here is no total void here. Now deflection will be a little bit, lateral load distribution will be little bit difficult here. So wherever you see that lateral load distribution is difficult there, then you apply semi-rigid diaphragm. But if it's clean like this building, then you can apply rigid diaphragm. Okay. This is for rigid diaphragm. Now let's go to our structural response and result interpretation in ETABS. Now, structural response refers to how the a building or structure react to a applied load. That applied load might be gravity load or lateral load. Gravity load, we already discussed that gravity load are dead load, self weight, wall load, and live load, and lateral load are wind and seismic load. And what are the structural response? The displacement of the building, drift of the building, modal parameter, inertial forces, and stress distribution are the structural response. While designing a building, we do check these three as a ETABS as a structural parameter that need to be within limit before designing the element at analysis stage. So what are these and how they dealt? How are they dealt in ETABS? Let's go to the drift and displacement first. What is displacement? Displacement is the overall movement of a point in the structure from its original position due to applied load. Right? And drift is the relative horizontal movement between two consecutive floors of a structure. Here, this total, just a minute. This total deflection each floor, we can say deflection of each floor relative to the base is deflection or displacement. And what is drift? Drift here is the relative displacement between two floors. Let's assume that's delta 1 and this is a delta 2. Then drift of this floor is delta 2 minus delta 1. And generally in ETABS, we do check drift ratio rather than drift. That drift ratio is the drift divided by respective floor height. Let's say this height here, right? Now, what are the codal parameters? If we see the 1893-2016 here, story drift in any story shall not exceed 0.004 times the story height. Means 0.004 into story height shall not exceed, should not be less than delta 2 minus delta 1. If you see, as buildings height is variable, so if we keep this here, then we need to check with 0.004. So extra work we need not to do there. So this every floor's drift and displacement should be checked with this limit. For seismic load, for wind load, it is given F by 500, which is 0.002. So if we see in ETABS how it is done, if we run the model and go to display story response plot, Here are maximum story displacement in x direction and max mean we consider here, and also y direction we consider here. So this is displacement. Displacement can be taken as that 0.004 into whole height of the building. That can be the limit. We check with this maximum value. Here it is given maximum value here. If it is coming under our limit, then we let it go and go further to design step. If it is exceeding, we need to make the building more step. We need to increase column size, beam size, or shear wall. We need to add shear wall. Now for drift, it is giving drift ratio here. Here it is coming that 0.003. It is within limit. So if it is exceeding, we need to again increase or stiffen the model further. I hope this is clear. Now, what are model parameters? This is the most important part of the while we design the structure. What are the codal parameters that what we need to check during design? These are all the code clause here. What we need to consider is the natural period of the fundamental torsional mode of the oscillation shall be smaller than those of the first two translational mode. Here it is saying that there are generally, when you read structural dynamics, there will be coming the new term like mode shape and model mode numbers, single degree of freedom, multi degree of freedom. So I'm giving just introduction only, is we have a limited time. When just you now assume, if you haven't read structural dynamics yet, just assume that there are a number of modes that are the deflection pattern, how they react during seismic force while vibrating, how they react. There are first mode, second mode, third mode, and generally ETABS in default analysis for 12 mode. Let's assume that 1, 2, 3. These first two modes should be translational. It is saying that the deformation pattern should be such that whenever the eccentricity becomes less, the first mode and second mode will be translation. It will be deflect in this direction only in one mode, and another mode in this direction only. And third mode will be torsional. It will rotate. We can see in model in a while. It is saying that first two modes should be translational and last mode third mode should be rotational. This is one criteria. Another criteria is total number of modes should be considered in such a way that the sum of this all mass participating mode should be 90%, at least 90%. This is one. And another one is here, the last mode that is considering this 90% mass participation should be less than 33 hours. The time period of the building should be greater than 0.03. So, and another is first three modes should be 65%. First three modes should be combinedly contribute to withheld this 65% of the mass participate. We'll see the table, then we can more visualize that part later. And another is the time period of first and second mode, two principal direction are away from by 10% of the higher mode. Now, general thing need to be considered about is time period should be by 10% difference. Now, another thing while designing we should know about model period is general time period of the building. The reference time period is generally, if we are designing 10-story building, you can say the reference time period, the time period of this building should be around 0.1 times n. Not exactly that, because the time period depends on the stiffness also. So this is like thumb rule. It should be around 0.1 into number of story. If we are designing 11 story, then it should be 1.1 second, something like that. Then if we are getting too much higher time period, then the model is too much stiff. There should be a mistake in a model, like while drawing beam or something other member, we might have disconnected that member with another or structure that is not freely moving. We can check that if we are getting lakhs of time period, sometimes it comes like that, then there might be some disconnected member. If we are getting lesser time period, just imagine that the time period is 0, then we might have applied all the fixed support in or hinge support in all story rather than giving in base. These and these are the common mistake we can find common mistake we can do in model while modeling part. We can find out by seeing the result of this model result. Let's go to how it is done in ETABS. We go to display, show table, here, show table, and then we go to model information. We click plus here, and then we go to model information and this table. This table gives us most part of the model analysis result. Here we let's go from first here. First two mode, if you see here, it is getting 82%. It is getting second model. So it was too much pretty symmetric, so we are getting higher. It might be lesser also sometimes. We are getting too much pretty good result here. So first two mode are getting in UX and UY direction. First mode is deflecting in Y direction. Second mode it is deflecting in X direction. And this RZ is giving us rotational. This before I was saying how it is deflecting, this way or rotational. If we achieve higher mass participation in X and Y direction, then it is the translational motion. And when we are getting RZ value higher, then it is dominating torsional motion. So here what we are getting is, in third mode we are getting torsional mode. In first mode, the building is translating along Y direction, and in the second mode, building is translating as in X direction. So whatever the code require, we are getting in this result. First two mode translation, third mode rotational. This is one part, right? And another is we saw here 33 hours. This part, if we see this last mode, it is given time period. What is frequency? 1 by t, right? If you reverse that, it is coming a frequency. This time period should not be lesser than 0.03. If it is getting lesser than 0.03, we need to do rigorous analysis to consider model mass correction, something like that. There is a option in ETABS itself how to do that, so I'll demonstrate that also. This is another part. We are getting greater than 33 hours, so we are getting lesser than 33 hours. This is also okay for now. Another part is first three modes should cross 65%. Here was this 65% mass participation. This is we are getting 83% in both mode, so this is also achieved in this part. And another is at least 90% participation should be in the model in last mode. Here we are getting 98%. It is okay here in 3 mode, right? And then another important point is these two principal directional modes should be departed by, here we are getting 0.471, 0.471. Here it is not, we haven't achieved this part. The time period should be departed by or different by 10%, at least 10%. As this building is too much symmetrical, in real field we do not have such type of building because some stair will be there or something like that. So or something like that, then it will come. This time period will be different. If we are not being able to make this difference, we need to do what is, we can stiffen the one direction more or something like that. We can do rectangular column in one direction, then it is becoming more steep in one direction. It will be this time period will be obviously changed. Otherwise, we can do beam depth in one direction, increase or decrease. So we can do is we can use rectangular column, or we can increase or decrease, change the beam dimension in one direction. Otherwise, we can add some shear wall in one direction, so that this time period will be aparted by 10%. These are the model parameter we check in ETABS. Now uh, some irregularity. It is about to complete now. Only one slide is remaining, I think. Then we will go to Q&A session. Some other thing, other data to be interpreted in ETABS are irregularity. Most of the irregularities given in 1893-2016 are visible one. We they do not need analysis. Just by drawing, we can see, just like re-entrant corner is here. It is given like 15% of whole dimension should not exceed this 15% or something like that. There is large opening or not, but there is a floating column or not, something like that. There are a lot of things that are that can be considered by seeing the drawing. Now, what are the things that need to be done in ETABS to find out those irregularity, if there is this irregularity exists or not? One is torsional irregularity. If we saw just here, if this mode of this some RZ is participating in third mode, in first two mode, the participation is too much less. Let's say less than 5%. There will not be a torsion. We can get that idea from that model result also. The benefit of model result is that even without we have prepared geometry in ETABS, we run without applying load. It gives the idea, because this model parameter does not depend on the mass matrix, so only stiffness matrix is required there. So before applying load also, we can get many more idea from this model result. So in torsional irregularity, what it is given here is we'll go to us there in another slide. There is explanation. First, let us understand the torsional those irregularities. And it is torsional irregularity. What is it? This point, the point of the deflection here and here. Let's say this is a building. When lateral load acts, if stiffness of the building is not distributed symmetrically, the deflection will be coming. Building will deflect like this, right? The maximum deflection to minimum deflection ratio should not be greater than 1.5. I think in NBC and IS it is little bit different. 1.5. Torsional irregularity. Yeah. Should not be the max by mean deflection should be less than 1.5. The ratio. And stiffness irregularity. The building along the height, the stiffness should be such that the stiffness of upper floor should not be greater than that of lower floor. Otherwise, the building failure pattern will be like collapse. It will collapse. The lower floor will be fail and upper floor will be strong. Then the column and this shear wall will fail in lower floor, and then whole building will be collapsed. So that building is designed in such a way that the stiffness of lower floor should be always greater or equal to upper floor. That is one. And mass irregularity. Another is mass irregularity. Mass irregularity is that when the mass of upper floor should not be greater than 1.5 times than that of lower floor. This is considered. And before I was discussing this 5% extensive eccentricity, while another part we check is this center of mass and rigidity also. Now let's discuss this table. This table are we get from ETABS itself, show table, and I'll show that also. Here are the mass of the story. The Codal criteria is giving that the mass of this story should not be greater than that of 1.5 times of, it should be 1.5 lesser than 1.5 times of this. One is this. Upper floor mass should be less, should not be greater than 1.5 times the lower story. We check here from this table, center of mass and rigidity. And for eccentricity, yes, this was too much symmetric building, so we are getting same value. The eccentricity should be less than the, what is eccentricity? This XCM minus XCR by XCCM minus XCR by building dimension LX in X direction into 100%. Another YCCM minus YCR by LY into 100%. This should not be greater than 5%. If we are getting greater than 5% and building is within torsional limit, then what we can do is we can overwrite eccentricity. We can compel ETABS that you design extra this eccentricity also. I will show where it is done. And then also there is another table which give story stiffness. The story stiffness also is same case, which is giving this. The stiffness of lower floor should be same or greater than upper floor. We check this parameter from ETABS. These are the parameter what we check in ETABS. Now let's go to the ETABS. Just a minute. What we can do is we can overwrite eccentricity from here. Overwrite eccentricity. We can provide each story how much we are getting this difference. If it is exceeding 5%, this minus this, then we can overwrite eccentricity with each floor from overwrite eccentricity. For 8 floor, 7 floor, 6 floor, how much eccentric length we are getting by subtracting XCM minus XCR. We always keep positive value here. Then it is giving its absolute length. We can overwrite this. And then before I was saying, how do we check torsional irregularity? Here is, just let me run this model. We see the display on deform shape, and we see this EQX on and EQX, EQY both. Then we apply this. We go to the eccentric loading also. If here is EQX step number, and here is 1, 2, 3 we are getting here. What is that? Here if we see step number 1 is without eccentricity, step number 2 is with eccentricity plus eccentricity, another is minus eccentricity. So we are getting 3 steps. So we check for all these steps. So we can go check here. Deflection is 58 mm. Here another is 50 mm. And this ratio 58 divided by 50 should not be greater than 1.5. If it is greater than 1.5, the code gives that if it is in the range of 1.5 to 1.5 to 2, then we can do dynamic analysis, no need to do other. If it is exceeding 2, the ratio is, if the ratio is exceeding 2, then we need to reconfigure the building, or we need to make within that limit by changing architectural drawing or position of shear wall or aiding column or something like that. And this concludes my presentation. Thank you. If any question, we can discuss here now. I hope this presentation helped you for understanding little bit on structural part. Thank
Thank
you.
you so much, sir, for this insightful presentation. Now I want to ask the student if you have any query, then please ask.
Uh, Sir, I wanted to ask if P delta analysis is required for like horizontal members, for example, beam. Do we have to?
Generally, P delta analysis. Uh, if you are designing only single element, it is another part. While designing building, it is the effect of that whole effect will become towards column also. That increased movement and deflection will give that effect to beam also and column also and shear wall also. That movement and shear force, increased movement and shear force will distribute it through whole beam, shear wall and column. So it is considered while designing horizontal member also during design. The effect is considered there also.
Hello, sir. I am having one question.
Yeah.
Sir, does this method can be used for lateral load on piles in order to find that lateral load on the pile?
In pile, I think it is already considered. Yeah.
Okay, okay, sir. Thank you.
Anyone else?
Good evening, sir.
Good evening.
Actually, I want to ask, like, usually we need to refer that earthquake loading, that IS 1893 for this, our codal provision.
Yeah.
Like you earlier told, like there is no specific specifications for this, like P delta type of analysis for our structures. So it's usually we will go with IS 1893 mostly. Ductile
Yeah.
detailing, I think. Is it
Sorry,
so?
can you ask again? I couldn't get your question.
So actually, I want to ask, like, we usually refer to IS 1890. There's ductile detailing for this kind of
Yeah.
analysis.
Yeah.
So is there any other code, Indian code, which we can refer for such type of analysis,
You know, for
or is it
tall,
like
yeah, for tall building, another code is available there. 16700,
okay,
2023. This should be also considered, but while designing using this 1893 also, we need to consider P delta analysis for high rise building.
okay, thank you, sir. So there is one more thing, like in IS 1893, we do have that, where we need to do the earthquake analysis. Like it has got one clause, I think, like above 15 stories or more than 2 stories. We in seismic zone 4, like below seismic zone 2, I think means we don't do that analysis.
Yeah.
So is it like is there any specification of P delta or the analysis like that we do in structure analysis in that code, or is it like we need to refer something like research papers only for these kind of
No,
things?
no. P delta analysis we can go directly through code, but what is here is for what type of building we need to consider P delta. Generally, for seismic zone 5 and 4, I think the code has given some parameter, but not like that stability index. We can check through ASC code or Euro code for that.
Okay, okay. Thank you, sir.
Sir, I have one question. Sir, you mentioned that in case a structure fails in P delta analysis, I was wondering how to like troubleshoot or figure out what is wrong. For example, I sometimes encounter negative stiffness. So how do we understand like what the problem is in that case?
I didn't say that P delta analysis is only additional. It is giving only additional moment or something like that. But while doing nonlinear analysis, either it is P delta or something pushover analysis and all, there is a convergence tolerance. Sometimes higher convergence tolerance, the ETABS cannot capture that. So at that time, we need to decrease that convergence tolerance, convergence tolerance. But if the building is failing, we need to increase the size and all. The size is not sufficient. We can say that.
Okay, thank you, sir.
थैंक यू सर। सर एक चीज़ और, जैसे आपका जो एक्सपीरियंस है 10+ ईयर से आप काम कर रहे हैं इंडस्ट्री में, स्ट्रक्चरल इंजीनियरिंग में, स्ट्रक्चरल डिजाइन कर रहे हैं, तो क्या सर आपको क्या ऐसा कभी लगा है कि जो 5 या 10 साल पहले सिनारियो थी स्ट्रक्चरल इंजीनियर की, आज वैसी नहीं, या फिर बढ़ी, या फिर मार्केट सेचुरेट हो गया है? क्या आप
ऐसा है कि ये सिविल एंड स्ट्रक्चर का तो कभी भी स्कोप नहीं खत्म होगा ये तो मैं कह सकता हूँ। बट ऐसा है कि पहले जब हम करियर शुरू कर रहे थे इतने डेप्थ में नहीं जाते थे सर। देयर वाज नॉट कोडल प्रोविजन आल्सो। दिस कोड आर रिवाइजिंग डे बाय डे। आई थिंक रिसेंटली we are getting now 1893 revised version also in 2024. I think draft has been already developed. Now they are giving lot of condition to be checked before some things. Now we are checking. That was not part of design. So structural engineering में बहुत advancement तो हुआ है, but as you said that saturation and all, if you are dedicated, so this scope will not end. I think in this field, एक तो ये क्या होता है कि डेवलपमेंट ऑलवेज होता ही रहेगा। कंस्ट्रक्शन तो होना ही है, पुराना बिल्डिंग डालेगा और नया बनेगा, हाई राइज होगा, ऐसा ही होता रहेगा। ये स्कोप तो मेरे हिसाब से बढ़ता ही जाएगा सर।
सर एक मेरा क्वेश्चन था सर, जैसे हम मोनोलिथिक स्टिफनेस के लिए हम डायफ्राम मॉडल करते हैं ना, इस में मतलब मोनोलिथिक फैक्ट के लिए हम डायफ्राम लगाते हैं माथ मॉडल। सर मेरा क्वेश्चन ये था कि अगर हमको जैसे वॉल की स्टिफनेस अगर हमको कंसीडर करनी है, अगर हम बिल्डिंग की मतलब फ्रेम मॉडल किए हैं, लेकिन हमने जो वॉल बनाई है वो हमारी वॉल सिग्निफिकेंट स्टिफनेस की है, अगर हम उसको अपने मॉडल में कंसीडर करना चाहते हैं तो हम उसको कैसे मॉडल करेंगे अपने मॉडलिंग में?
नहीं वो तो वॉल ही मॉडल करेंगे हम। नहीं,
जैसे अभी करेंटली क्या होता है कि हम वॉल का लोड लगा लेते हैं, जैसे हमारे
आप कह रहे हैं कि शेयर वॉल नहीं, वो ब्रिक वॉल
नहीं है। यस सर, ब्रिक वॉल की स्टिफनेस हम कैसे अपने मॉडल में?
उसके लिए तो हम स्ट्रट एंड टाई मॉडल करना पड़ेगा। वो कोड में है, उसका फॉर्मूला भी है। अगर वॉल का विड्थ अगर ओपनिंग होगा तो लिटिल बिट कॉम्प्लिकेटेड हो जाएगा उधर। अगर ओपनिंग नहीं होगा तो कोड ने भी दिया हुआ है कि दैट उसका विड्थ कितना होना चाहिए, डेप्थ कितना होना चाहिए। स्ट्रट एंड टाई मॉडल कहते हैं उसे।
सर अलग से जैसे डायफ्राम के लिए जैसे उन्होंने एक प्रोविजन बना के टैक्स में दिया है, क्या इसके लिए कोई अलग से उन्होंने कुछ ऐसा डिफाइन किया है?
एज अ लिंक हम ड्रॉ कर सकते हैं, लिंक एलिमेंट हम ड्रॉ कर सकते हैं। और लिंक नहीं, वो लिंक एलिमेंट होता है ETABS में,
इलास्टिक लिंक टाइप का।
हाँ, उसमें हम हमारा स्ट्रट का वो पैरामीटर डाल के वो कर सकते हैं उसमें।
ओके। एंड सर एक मतलब क्वेश्चन था, वो हम कोई बीम हमको मॉडल करनी है एज ए इलास्टिक फाउंडेशन, मतलब इलास्टिक फाउंडेशन पे हमको एक बीम मॉडल करनी है, तो वो हम कैसे मॉडल करते हैं अपने ETABS में, सैप में?
हम जनरली मैं क्या करता हूँ कि फाउंडेशन में सेफ में करता हूँ। CSI का अनदर सॉफ्टवेयर है, CSI उसमें मॉडल कर सकते हैं। वो इजीली इलास्टिक एनालिसिस कर सकता है, फ्लेक्सिबल एज अ फ्लेक्सिबल फाउंडेशन।
मतलब उसको एज ए फ्लेक्सिबल फाउंडेशन ही मॉडल डायरेक्ट मॉडल करेंगे या फिर उसमें कुछ
नहीं डायरेक्ट मॉडल करेंगे, उसमें सॉइल सबग्रेड मॉडुलस डालेंगे उधर,
ओके
तो उस वो अपने आप ही एज अ फ्लेक्सिबल फाउंडेशन ट्रीट करेगा।
सर एक्चुअली जैसे फाउंडेशन दो टाइप हो ना, एक रिजिड फाउंडेशन एंड एक फ्लेक्सिबल। अब हमको क्या करना है ना, हमको बीम, हमारी जो बीम है वो भी इलास्टिक है एंड हमारा फाउंडेशन भी इलास्टिक है।
नहीं हम एफईएम मॉडल करते हैं और सॉइल सबग्रेड मॉडुलस डालते हैं तो ऑब्वियसली इलास्टिक हो जाएगा, नॉट रिजिड।
ओके ओके
फॉर
सर।
रिजिड वी जस्ट व्हाट डू इज मैन्युअली, हम जैसे बुक में पढ़ा है ना, तो लोड आएगा इधर से बेयरिंग कैपेसिटी आएगा तो पी बाई एस बी सी करके ये निकालते हैं ना,
यस सर।
वो तो रिजिड फाउंडेशन का कंसेप्ट हो गया। अगर हम सॉइल सबग्रेड मॉडुलस डाल के उसका ईच एंड एवरी पॉइंट पे सॉइल प्रेशर देखते हैं तो वो फ्लेक्सिबल फाउंडेशन।
ओके एंड सर एक क्वेश्चन था कि हम बेस ईयर करेक्शन लगाते हैं ना इसमें,
हाँ
सर वो क्यों लगाते हैं और कैसे लगाते हैं, वो थोड़ा सा पूछना था सर।
बेस ईयर करेक्शन आप बोल रहे हैं कि स्केलिंग फैक्टर हम यूज करते हैं?
या वो जो जी का वैल्यू 9.8
क्या
हम
होता है कि हम इनिशियल फैक्टर, ये क्या होता है कि फर्स्ट हम क्या समझना पड़ता है कि हम पहले सेस्मिक फोर्स के लिए बेस शेयर निकालते हैं, राइट?
ओके सर।
बेस शेयर हम कैसे निकालते हैं कि वहां का पीजीए होता है, उधर का सॉइल टाइप होता है, इम्पोर्टेंस फैक्टर होता है
यस सर।
उस लोकेशन का,
यस सर।
उसको कंसीडर करके हम एक बेस शेयर निकालते हैं।
ओके।
पर डायनामिक एनालिसिस में तो वैसा कुछ भी नहीं होता है वो पैरामीटर।
यस सर।
वो तो जस्ट नॉर्मलाइज्ड पैटर्न ओनली है वो तो।
यस सर।
So to match that base here, we scale up. And this response spectrum में हम स्केल करते हैं।
सर वो हम वही पूछना चाह रहे हैं कि जैसे हम इनिशियल एक 9.81 का फैक्टर लेके चलते हैं,
वो चलना नहीं पड़ता है एक्चुअली व्हेन डिजाइनिंग रियल फील्ड। फर्स्ट आप मॉडल कीजिए, रेस्पॉन्स स्पेक्ट्रम लोड केस डिफाइन कीजिए और केस डिफाइन कीजिए।
सर सॉरी मैं अभी रिस्पांस स्पेक्ट्रम नहीं देख रहा, मैं स्टैटिक बेस ईयर की बात कर रहा हूँ। स्टैटिक कंडीशन में हम अर्थक्वेक लोड एनालिसिस कर रहे हैं, तो उसमें जब हम इनिशियल उसको लेके चलते हैं तो 9.81 हम
नहीं वो रेस्पॉन्स स्पेक्ट्रम ही है आप जो कह रहे हैं 9.81। मैं स्क्रीन शेयर करके दिखाता हूँ आपको।
यस सर, एक बार थोड़ा क्लियर कर दीजिए सर।
वो रेस्पॉन्स स्पेक्ट्रम ही है आप जो बोल रहे हैं, इनिशियल स्केल फैक्टर बोल रहे होंगे आप।
या
डिफाइन में लोड केसेस में अगर हम जाएंगे तो न्यू केस में इधर रेस्पॉन्स स्पेक्ट्रम डाल के इधर हम 19860 डालते हैं। ये कह रहे हैं
सर। हाँ हाँ
वो ये तो रेस्पॉन्स स्पेक्ट्रम ही हो गया।
ओके सर, तो यहाँ पे सर हम
डालिए 1 डालिए कुछ फर्क नहीं पड़ेगा। लास्ट में क्या करना है कि हमें क्या चेक करना है, मैं करके दिखाता हूँ।
हाँ सर थोड़ा सा इसको क्लियर करिए सर, इसमें थोड़ा डाउट होता है।
एड न्यू केस करता हूँ एक फॉर RSX ओनली, लेट्स कंसीडर।
ओके सर।
सिमिलर विल बी फॉर RSY आल्सो। RSX में करता हूँ रेस्पॉन्स स्पेक्ट्रम एड न्यू केस फॉर X U1 फॉर Y U2 हम डालते हैं। यहाँ हमें पहले एक फंक्शन डिफाइन करना पड़ता है। लेट्स डिफाइन दैट फंक्शन आल्सो ड्यूरिंग रेस्पॉन्स स्पेक्ट्रम। डिफाइन फंक्शन रेस्पॉन्स स्पेक्ट्रम, इंडियन कोड का फंक्शन डिफॉल्ट है इधर, ये ऐड कर देंगे। IS कौन सी जोन में है इधर अभी डिफॉल्ट डाल देते हैं। अब यहाँ इधर क्या करते हैं कि रेस्पॉन्स स्पेक्ट्रम में हम ये IS डालते हैं। अब इधर जो भी डाटा डालो आपको, मैं अब 552 कर देता हूँ। हमारा मेन मोटिव क्या है कि दोनों का बेस शेयर मैच होना चाहिए, वही है मोटिव। बट इनिशियल स्केल फैक्टर इज 9810 नहीं, वो IG/2R कहते हैं उसे। IG/2R करके जो वैल्यू आता है उससे हम दैट ड्रिफ्ट डिस्प्लेसमेंट चेक कर सकते हैं। और स्केल वी डू नॉट चेक दैट रेस्पॉन्स फॉर रेस्पॉन्स स्पेक्ट्रम फॉर ऑन स्केल इनिशियल स्केल फैक्टर वो करते हैं। अब हम क्या करते हैं कि इधर से डिस्प्ले में जाके शो टेबल में जाके स्ट्रक्चरल आउटपुट में बेस रिएक्शन देखते हैं। इधर
Yes, sir.
रेस्पॉन्स स्पेक्ट्रम और एक्स का देखे अभी देखेंगे तो अब ये बेस शेयर क्या हो रहा है कि EQX में 759 आ रहा है,
Okay, sir.
रेस्पॉन्स स्पेक्ट्रम में 20 आ रहा है। ये
Yes, sir.
दोनों सेम होना चाहिए। ये दोनों सेम होने के लिए हम क्या निकालते हैं कि एक मल्टीप्लिकेशन फैक्टर निकालते हैं।
Yes, sir.
सो अगर आप उधर 552 डाल रहे हैं, इधर इस फिर 20 आ रहा है। अगर वहाँ 98 समथिंग डालेंगे, इधर हायर वैल्यू आएगा। पर हमारा मेन मोटिव तो क्या है कि ये मल्टीप्लिकेशन फैक्टर निकालना है। स्टैटिक डिवाइड बाय डायनामिक करते हैं, ये फैक्टर लेके उधर डिवाइड मल्टीप्लाई कर देते हैं इधर डिफाइन में, लोड केस में। सो अल्टीमेट वैल्यू क्या हो जाता है कि ये इधर मल्टीप्लाई करके ये वैल्यू निकालते हैं इधर।
सर ये जो इनिशियल केस जो लेके चलते हैं, इससे मतलब सर ये सब पढ़ने के लिए कोई डॉक्यूमेंट कुछ है क्या कहीं पे, या फिर
आप सर्च कर सकते हैं। पर इनिशियल का इफ योर मेन मोटिव इज टू डू डायनामिक एनालिसिस, इनिशियल फैक्टर का कोई वजह नहीं है। जोन सी वैल्यू डाल के जा सकते हैं, पर IG/2R कोड कहता है।
ओके
ये करेंगे, अब रन करेंगे तो उधर वन स्टेप में ही वो स्केल हो जाएगा, सेम बेस शेयर हो जाएगा। तो आप फर्दर डिजाइन कर सकते हैं। अभी देखते हैं। अब दोनों सेम हो गए।
यस सर।
हमारा मोटिव ही है ये। अगर आप इनिशियल फैक्टर में जो डालिए, ये रेशियो फर्क आना है, अल्टीमेटली बेस शेयर मैच हो जाएगा।
सर एक क्वेश्चन और था कि इसको हम इक्वल करते क्यों हैं? अगर हमारे स्टैटिक कंडीशन में अगर ज्यादा आ रहा है या फिर रिस्पांस फैक्टर में अगर ज्यादा आ रहा है, तो सच में वो वैसे ही स्ट्रक्चर को वैसे ही डैमेज करेगा ना फिर?
नहीं, वो क्या होता है कि हम साइट स्पेसिफिक इतना मैं अभी बोला कि PGA होता है, उससे करके बेस शेयर आना ही तो वही बेस शेयर है, उससे ज्यादा तो नहीं आएगा। हमने टोटल बेस शेयर तो कैलकुलेट कर चुके हैं स्टैटिक में।
सर
तो वही बेस शेयर के लिए स्केल अप करके हम डायनामिक करते हैं। डायनामिक में क्या होता है कि वो तो अगर आपने स्ट्रक्चरल डायनामिक्स पढ़ा हुआ है तो हम क्या करते हैं, डिफॉर्म शेप ऐसे करते हैं, आपको याद होगा। ये वैल्यू 1 लेके करते हैं ना।
ओके सर।
हाँ, ये वैल्यू 1 लेके करते हैं। ये तो नॉर्मलाइज है।
यस सर।
बेस शेयर से इसको स्केल अप करना है।
ओके ओके।
स्केल अप तो करना पड़ता है, बेस शेयर मैच करना है।
सर एक क्वेश्चन और था जो थोड़ा सा डाउटफुल है मेरा।
हाँ।
कि अक्सर जैसे मैंने देखा भी है और एक दो लोगों ने हमको बताया भी था, जो हमारा बेस शेयर आता है वो स्टैटिक केस में मैक्सिमम आता है। अगर हम रिस्पांस स्पेक्ट्रम से अगर हम बेस शेयर निकालते हैं और हम बेसिक स्टैटिक कंडीशन में देखते हैं तो हमारा स्टैटिक कंडीशन में बेस शेयर मैक्सिमम आता है। क्या ऐसा मतलब होता है या फिर?
नहीं, वो क्या है कि बेस शेयर का इनिशियल स्पेल फैक्टर में समथिंग आएगा। अगर वो तो टोटली डिपेंड होगा कि आपने फर्स्ट में स्केल फैक्टर कितना डाला है। 1 डालेंगे तो ऑब्वियसली उससे कम आएगा स्टैटिक से। 1000 डालेंगे तो ज्यादा आएगा रेस्पॉन्स स्पेक्ट्रम में, राइट?
ओके।
तो उससे मैटर नहीं करता। हमें मेन टारगेट क्या है कि स्टैटिक का बेस शेयर से रेस्पॉन्स का मैच करना है। ये तो एक पैटर्न है, ओनली इट इज अ पैटर्न, राइट? सो आगे अब प्रीवियसली मैंने बोला कि अगर ये देखेंगे तो एक और देखेंगे तो समझेंगे आप। यहाँ के इधर क्या हो रहा है कि ये 82% दिख रहा है ना।
यस सर।
ये 82% तो अब स्टैटिक बेस शेयर से मल्टीप्लाई करेगा ना वो।
यस सर।
उतना मास के लिए फर्स्ट मोड में डिजाइन होगा।
ओके।
तो इन सब मोड को मर्ज करके CQC और SRSS मेथड से टोटल बेस शेयर निकाल के डिजाइन करता है।
ओके ओके। सर आपने एक चीज और इसमें स्लाइड में आपने शायद मेंशन किया था कहीं पे कि जो हमारा टोटल मॉडल मास होगा वो टोटल मॉडल मास का 90% मैक्सिमम बेस मतलब यूटिलाइज होना चाहिए, मैक्सिमम 90%।
अगर हाँ वो तो है, कोड में ये बोला है। अगर 12 मोड में नहीं है तो नंबर ऑफ मोड बढ़ा सकते हैं हम।
ओके।
तो नंबर ऑफ मोड बढ़ाने के लिए हम किधर जाना पड़ता है कि अभी मैंने एक बार बोलूंगा क्या था, कहा था, भूल गया शायद। ये यहाँ जाके हम नंबर ऑफ मोड बढ़ा सकते हैं। अगर मैंने बोला था कि 33% अचीव नहीं हुआ तो क्या करना, इधर जाके हम
33% अचीव नहीं है, इसका मतलब कि वो होगा।
33 हॉर्स बोला था ना।
हाँ, इसका मतलब कि वो डायनेमिक मोड में जा ही नहीं रहा है फिर।
हाँ, तो 33 हॉर्स से ज्यादा आ गया तो कोड ने बोला है कि स्टैटिक करेक्शन करके कर सकते हैं। अगर आप एडवांस में जाके वो करेंगे तो यहाँ ऐड कर सकते हैं एक्सीलेशन डाल के इधर, यहाँ यूएक्स यूआई यूजेड में अब टारगेट मास रेशियो क्या कर देंगे आप, 90 ओवर कर देंगे, स्टैटिक करेक्शन को यस कर देंगे, तो वो अपने आप ही कर लेगा। इतने मोड में 90% अचीव करना ट्राई करेगा। अगर समथिंग नहीं पूरा तो आप इसको 18 समथिंग बढ़ा सकते हैं।
ओके सर, ओके सर, थैंक यू सर, थैंक यू सर।
Okay, thank you, sir. Thank you so much.
Thank you, Balkrishna sir. I would like to give a big thank for giving me this opportunity. If required, we can do this such session further also as per student demands. I will be always.
Sir, actually we will want.
Okay. We can do it also further.
Yes sir, it was very nice sir, very nice. Thanks.
Yeah, I hope it was fruitful.
Yes sir, I have one question. Actually sir, जब हम रिस्पॉन्स स्पेक्ट्रम एनालिसिस कर रहे हैं तो सर टाइम हिस्ट्री एनालिसिस क्यों करते हैं फिर? एक्चुअली उसमें भी रिस्पॉन्स स्पेक्ट्रम ऐड करते हैं।
वो क्या होता है कि टाइम हिस्ट्री एनालिसिस और रिस्पॉन्स स्पेक्ट्रम एनालिसिस दो डिफरेंट पार्ट है। डायनामिक एनालिसिस के अंतर्गत पड़ते हैं दोनों, रिस्पॉन्स स्पेक्ट्रम एंड टाइम हिस्ट्री एनालिसिस। टाइम हिस्ट्री एनालिसिस फॉर बिल्डिंग डिजाइन इट इज नॉट यूज, इट इज यूज फॉर रिसर्च पर्पज और रेट्रोफिट टेक्निक। अगर ये क्या होता है कि आपने 2015 में नेपाल में बहुत बड़ा अर्थक्वेक गया था, आपको शायद पता है या नहीं। अगर मेरा बिल्डिंग अभी चेक करना है कि अगर उतना अर्थक्वेक आएगा तो ये बिल्डिंग रेजिस्ट कर सकेगा कि नहीं उतना अर्थक्वेक को, तो वैसे कंडीशन में हम टाइम हिस्ट्री एनालिसिस यूज करते हैं। अगर हमें सर्टन कोई अर्थक्वेक का डाटा है, अगर हमें चेक करना चाहते हैं कि उतना अर्थक्वेक ये बिल्डिंग रेजिस्ट कर सकता है कि नहीं, वो वैसे टाइम में टाइम हिस्ट्री कर सकते हैं। मगर डिजाइन में ये डायनामिक और अदर तो करना ही पड़ेगा। ये पीक के लिए होता है टाइम हिस्ट्री, तो बस वो सर्टन अर्थक्वेक एल सेंट्रो कहते हैं, चीची कहते हैं, सम फेमस अर्थक्वेक डाटा है हमारे पास। ये बिल्डिंग उतना अर्थक्वेक रेजिस्ट कर सकता है कि नहीं, वो चेक करने के लिए हम यूज करते हैं टाइम हिस्ट्री। बेसिकली इट इज मोर रिसर्च पर्पज रादर देन डिजाइन फॉर टाइम हिस्ट्री।
तो सर एक्चुअली यदि हम कोई बिल्डिंग डिजाइन करते हैं तो उसके लिए रिस्पॉन्स स्पेक्ट्रम इनफ है, मतलब डिजाइन के लिए?
डिजाइन को लिए तो रिस्पॉन्स स्पेक्ट्रम ही इनफ है।
ओके सर।
ठीक है, थैंक यू सर। अब टाइम बहुत हो गया।
Okay, thank you, Balkrishna sir, for this opportunity.
ठीक है, गुड नाइट
Okay,
सर।
good night.